7.6 is about a theorem called Bayes' theorem. So this is part 1. So I draw the tree that's on the handout on the board. So we see that we have either A or A complement is our first event. And then from there, you have a second event that is either B or B complement, B or B complement. So in the previous section, 7.5, what we looked at is the probability of B occurring given that A has already occurred. So we're looking for B given that A has already happened. So we're looking for something on the right side given the left side has already happened. So right versus left. Now in section 7.6, that's going to flip on us. So we're now looking for the probability of A given B has already happened. So this time we're looking for the probability of left given that the right has already occurred. So it's a slightly different twist to it. So our first example is going to do this kind of conditional probability off of a Venn diagram, which we have not done yet. So this is our first example. So example 1. So refer to the accompanying Venn diagram, an experiment in which 3 mutually exclusive events, A, B, and C, form a partition of the sample space. So we're going to take our sample space and divide it into 3 events. So here's A, here's B, here's C. They are mutually exclusive, meaning all 3 of them cannot occur together. They have no intersection. Okay, we also know that within those events, we've got either D or complement happening. So here's our set D. This is 20 out of 50, sorry. This is 30. This is 25, 15. Over here is 15 and 20, and then this is the sample space altogether. So you'll notice that we have a D and we have outside of D, which would be D complement. So inside of C, we have both D and D complement. Inside of B, we see both D and D complement. Inside of A, we have an A, we have D and also A complement. If we add all our numbers together, because we're looking at probabilities, we need that sum. So the sum inside the Venn diagram is 125. And that's simply 25 plus 20 plus 15 plus 15 plus 30 plus 20. Okay, and again, they are mutually exclusive, which is somewhat important here. So the first thing they ask us for is the number inside of A. This is just to lay groundwork. So inside of A, we can see we have 40. That was the 25 and the 15 added together. The number inside of B is the 20 and the 30 added together, which is 50. The number inside of C is 15 and 20, which is 35. The number in the sample space we already found, but we know that's 125 if we add all those numbers together. The number inside of D, so D is this set. Well, that's 25, 20 plus 15. So that would be 40 plus 20, which is 60. And the number in D complement, well, D and D complement make up the sample space. So 60 from 125 is 65. I could also find that by adding 20, 30, and 15 together. So that's just that raw counts on the numbers. Okay, using the information given in the Venn diagram, let's draw a tree that illustrates that Venn diagram and the probabilities of A, B, and C. So we're going to start off with the first branching at A, B, and C. And then from that, we're going to do the branching of D, D complement, D, D complement, D, and D complement. So you'll notice that D and D complement happen inside of A and inside of B and inside of C. But A and C can't branch off of each other. So it really is telling me how to draw this Venn diagram. Okay, so in terms of numbers, we know that A was 40 out of 125. We know that B was 50 out of 125. And C is the remaining 35 out of 125. Okay, now D happens inside of A. So this branching on D is just what's inside of A. So that would be 25 out of the 40 that are inside of A. So notice that it wasn't the overall total. It's just the 25 out of the 40 that happened inside of A. And then this would be the 15 out of the 40, the remaining 15. Do the same thing for B and C. So B has 20 out of 50 that are inside of D. D complement is 30 out of 50. Inside of C, we've got 15 out of 35. And the complement is 20 out of 35. So there is the tree that matches the Venn diagram. That's a first for us. We haven't done that before. Okay, now that we have that, let's go find some information. So Part A was just to draw the tree. There's our tree. B is asking us to find the probability of D. So I can definitely come in and do the same thing we did in the previous section. I can multiply across and add down. I can also look at the fact that back up here, I know that D is 60 out of the total of 125. So I can just take the 60 and divide it by 125. That is the same answer I would get if I took 40 out of 125 times 25 out of 40, plus 50 out of 125 times 20 out of 50, plus 35 out of 125 times the 15 out of 35. I'd get the same answer, believe it or not. But because I've got these individual numbers, I'm going to go the easier route. And that comes out to be 0.48. A lot of times we don't have those individual numbers, so we wouldn't be able to do that. Okay, the next one's asking me for the probability of B given D. Okay, so for the first time, we're looking for something on the left side given the right side. Well, I'm going to use the formula. The formula says to find their intersection. So that would be the probability of B intersect D divided by the probability of D. Okay, well, B intersect D, that would be this times this. So that's 50 over the 125 times 20 over 50. Divided by what I know has already happened, and we already know D is sitting right here, 60 over 125. Okay, if you're going to type this into your calculator, make sure you get parentheses around every fraction. You can take them to decimals if you want. It's up to you entirely. But if you do that, you actually end up with 20 out of 60, which gives me 1/3. 3, 3, 3. Okay, what if we look for the probability of D complement? Again, I can come in and multiply 40 over 125 times the 15 over 40, 50 over 125 times 30 over 50, 35 over 125 times 20 over 35, or I can use the fact that D complement is 65 out of the 125, which gives me 0.52. And then the final thing that they're asking for is the probability of B given D complement. So this time we need the intersection of B and D complement. B intersect D complement. All over what we know has already happened, which is D complement. So we'll take the intersection, which is the bottom branching. So 35 over 125 times 30 over 35. All over D complement we just found, which was 65 over 125. I'm going to do some canceling. These guys cancel. So I get 30 over 65, which comes out to be 0.462. So that's using the conditional probability theorem, right? That's using the statement that we learned in the previous section.